So this is a lecture on limiting reactants, and we talked about this a little bit in class when we looked at the fire and the oxygen, and when you put a glass beaker on top of the fire, it goes out because the oxygen runs out, etc. and so forth. So we're going to talk about limiting reactants now. Please remember to pay close attention to this lecture because we're going to do the problems in class. So the first concept is that rarely reactants in a chemical reaction are present in the exact mole ratio specified in the balance equation. So what that means is usually you don't have the exact amount of ingredients, let's say. So for example, when you're baking cookies or a cake, usually you're measuring out the ingredients you need, but you definitely have leftover flour, leftover sugar, for example. So usually that's what happens during chemical reaction. You're not going to have the things in exact ratios. So what usually happens is one or more of the reactants is present in what we call excess meaning extra, and then the reaction proceeds until all of one reactant is used up. So if we went back to the cookie analogy, usually your mom or you have plenty of flour, plenty of sugar, so you take a cup or two out of those containers, but generally you only have one bag of chocolate chips. And you're going to use all those chocolate chips in your cookie. So the chocolate chips would be the example of the ingredient that is used all the way up. You use all of the chocolate chips. And the amount of chocolate chips you have kind of governs how many batches of cookies you can make. So you may have plenty of flour, plenty of sugar, but if you only have one bag of chocolate chips, you're only going to make one batch of cookies. The chocolate chips in that case will be something called the limiting reactant. This is the reactant that runs out and stops the reaction from going. So if you remember when we did the fire on the desk, I lit the fire, and first we just let the fire go out because all the ethanol ran out. There was no more liquid on the table. And then the second time I put a beaker over the fire, and the fire went out that time because the oxygen was used up. So in each of those cases, one, the ethanol was a limiting reactant, the other one, the oxygen is a limiting reactant. So we have the limiting reactant is the one that gets used up and stops the reaction. The leftovers, it could be one or more, are called the excess reactants. When you think of excess, think extra. So if I give you an analogy here of a toolkit, we have screwdrivers, pliers, and a hammer, and we're going to make a set. So you're making a tool set, let's say as a gift. So in each set you can have one pair of pliers, one hammer, and two screwdrivers. So you see here you can make, with the available ingredients or the available tools, you can make 4 complete sets to give people. So you can make 4 complete gifts. But if you count how many we had at the beginning, so you have 2, 4, 6, 8, 10 screwdrivers, 5 pair of pliers, and 4 hammers. Well, in this set, you have 2, 4, 6, 8 screwdrivers, 4 pliers, and 4 hammers. So what happens is, at the end, you've made 4 complete set of tools with 1 pair of pliers, 2 screwdrivers, 1 hammer, but you're going to have a pair of pliers and 2 screwdrivers left over from your starting materials. You ran out of hammers. You only have 4 hammers, and if each group just gets 1 hammer, that is what's going to stop you from making another complete set. So the reason why you can't make 5 sets is because you don't have another hammer. So the hammer in that case would be the limiting reactant, and the pliers and the screwdrivers, the leftover tools, would be the excess reactants. So we're going to do problems with this. Again, this is something that's used in industry where you want to figure out, what is the most possible amount of this product I can make, and it's going to depend on what the limiting reactant is. We pay most attention to the limiting reactant, we pay least attention to the excess. Because really, if you have extra, it doesn't really matter. The way where the excess can come into play is if, for example, waste, nuclear waste in particular, that has to go somewhere, so you really want to minimize what you have left over. So let's look at sample problem number 1. It says the reaction between solid white phosphorus and oxygen produces solid tetraphosphorus digoxide. This is often called diphosphorus pentoxide because of its empirical formula. So A, you're going to determine the mass of tetraphosphorus digoxide formed when you have 25 grams of phosphorus and 50 grams of oxygen, and then how much excess is left over. So like we were doing with all the stoic, your first step is to have a balanced equation. So you see here you have P4, the phosphorus, plus O2. It's going to make P4O10, and then you balance it. Make sure it is balanced. Second step is you're going to take both gram amounts in the problem and turn them to moles. So here is the key difference between stoic and limiting reactant. In limiting reactant problems, you're going to be given 2 starting amounts. In stoichiometry problems, you were only given 1, and that's when you can just use your mole-to-mole ratio, your train station, and convert. But in this case, you're going to be given 2 starting amounts. So this is how you're going to know you have to do this way instead of just straight stoich. So like a lot of things we've done, we're going to take the starting amounts and we're going to turn them to moles by dividing by the molar mass of the reactants. So I have 0.2 moles of the first reactant, P4, and 1.56 moles of the second reactant, O2. The next step is to determine which one is limiting, which one runs out first. So what you have to do is compare what you have to what you need. So what you need is going to come from that balanced equation and the mole ratio. So you see from this balanced equation, this one has a 1 as a coefficient, this one has a 5. So from this balanced equation, you need 5 times as much oxygen. So for every 1 mole of phosphorus, you need 5 times that amount moles of oxygen. So what you're going to figure out is this 5 times that? That's what we're figuring out. Do you have 5 times as much O2 as you do P4? So the way you do that is you're going to do a single mole-to-mole ratio problem where you start in moles and end in moles. Just as a constant, so we're all having the same work, you're going to pick the smallest mole amount, so just 0.2 moles of P4. You're going to use your mole-to-mole ratio and your coefficients to determine how much O2 you would need. So what we figured out is if you have 0.2 moles of P4, you would need 1 mole of O2 to react with that. That is exactly 5 times the amount. What we do with that number is compare it to what we had when we started. So if this means that when there are 0.2 moles of P4, we need 1 mole of O2. That is theoretical. That is the 5 times the amount. Since from the problem we know we have 1.56 moles, which is more, if you need 1 mole and you have 1.56 moles, you have plenty of oxygen. In fact, you have extra oxygen. You have more than enough. That means O2 is in excess, and P4 therefore is the limiting reactant by default. Since you only have 2 reactants, one has to be in excess, one has to be the limiting. And I'm only going to give you problems with two reactants. So this is how you figure it out. You take your amounts, you turn it to moles, you do a 1-step mole-to-mole ratio, and then you kind of determine how much do I have, how much do I need, and figure out which one is in excess and which one is limiting. From there, you're always going to use the limiting reactant to figure out product formed, because when the limiting reactant runs out, the reaction stops. So that's when the product stopped being formed. That's why you have to figure out the limiting reactant. So you're going to take your moles of limiting reactant as the given, as your start. You're going to use the factor label method and the mole ratio to get grams produced. And usually you're going to do grams produced, occasionally liters produced as your final product. So I'm going to take 0.2 moles of P4, my limiting reactant. I'm going to do a mole-to-mole ratio. And then I'm going to take moles of P4O10, multiply by its molar mass to get that answer in grams. And I figure out from this reaction you can get 56.78 grams of P4O10. Now part B does ask about O2 being in excess, and it's not asking how much is consumed, it's asking how much is left over, which is usually what they ask. So again, you're starting with the limiting reactant. The limiting reactant is very, very, very important. That is always your start in these problems. That is always your given. So I'm going to do moles of the limiting, P4, to the mole ratio to grams of O2. So we see 0.2 moles of P4, our mole ratio again, and then I'm going to use the molar mass of O2, 32, to get that you're going to use 32 grams of oxygen. That's how much is used. The problem said how much is left over. So when I go from the beginning, it says I started with 50 grams, 32 grams are used, so I have 18 grams in excess or left over. Chemical reactions, of course, do not always do exactly what you expect. We've seen that a bunch of times, all the way back to, our oil spill cleanup where you expected the density of water to be exactly 1, and a lot of you didn't get exactly 1, you were a little off. Remember, theoretical is the amount of product you should have produced. Theoretical is, in theory, what should be at the best case scenario. Actual is the amount that really happens. If you do this in an experiment, this is how much you would really get out. And then percent yield is a problem where you just compare these two values. You take actual over theoretical times 100. Very similar to percent error. So you can look at it that way, but just remember, A over T, it's alphabetical. Actual over theoretical. And that concludes this lecture.